school. Today we're very happy to have Guilherme Pimentel with us. So welcome, and please, the floor is yours.
Okay, thank you. So good morning. These lectures are about the beginning of the universe. I hope that that's interesting enough. So the birth of the universe and the initial conditions that are responsible for structure formation. Okay? It's a very peculiar moment in the history of the universe, its birth, because it's perhaps the only place in which quantum mechanics and gravity are equally important, with observational consequences. Of course, inside of black holes or near black holes, quantum mechanical effects are, we believe, well, it's interesting to study the quantum mechanics of black holes, but this has observational teeth, and you can go and test. I will, today, probably I'll just review what we know from theory that we can match onto observations, and then the other lectures are about theoretical speculation, how we go beyond the leading paradigm and how we compute more detailed observables. It involves some beautiful quantum field theory in curved space. The space-time is very curved. So there are new tools, new methods, and it's going to use, I was following the lectures of the first week, it's going to use some technology that was developed by Julio using scattering amplitudes. We're going to use some of conformal field theory, machinery, because there's some emergent conformal symmetry at the surface in which you set up these initial conditions. So I think it's a pretty beautiful topic. Of course, I'm biased because I work on it, but I hope I'll convince you. Okay, so let me start by drawing a picture. Usually time goes up for me, but I think that with this board, it would be nicer. By the way, if I write here in the bottom, do you see in the back, people? Okay, so. Okay, good. So here's time. And here we are. When I give this talk in the United States, you need to remind them that us is a world, not even though they think it's the US, but they're not. But anyway, so here we are. We observe. So cosmology is about observations. It's not about experiments in some sense. We just observe the universe, and we try to make sense of the observations. And then we need to infer from observations, need to tell some coherent story of the universe. And there are two main sources of cosmological information that we have. They mostly come from photons. Maybe one day we're going to get information from other probes, like you could dream about neutrinos or gravitational waves and so on, but almost everything we know comes from photons. And well, what are the main probes of our cosmology? One are galaxies. So these are my galaxies. After drawing these hundreds of times, I still haven't improved on my galaxy drawing skills. So these are my galaxies. Maybe they come in different shapes and so on. And they're distributed seemingly in a random pattern, but we believe that they are raisings on some scaffolding of dark matter. So this is my dark matter. So it forms some cosmic web, and there are halos and so on. You take a whole cosmology course to make sense of this story. So this is the large-scale. So when you look at the universe above, like I think 10 megaparsecs and so on, and if you look at the universe at very large scales, then we think that we're learning something about the cosmology. Okay, so this is the large scale structure of the universe. So this was historically not such a treasure trove of cosmological information, but now it's really where the future lies, at least in the next decade. There will be a lot of surveys mapping the universe with better and better accuracy, precision. And you will start getting competitive, and you could even dream that it's going to do better than historically what's been the major source of information, the microwave background, from which we almost squeezed all the juice. But here, there's still a lot of room for improvement in terms of cataloging where every galaxy, doing a whole census of all the galaxies in the universe. We're still probably a factor of 100 or so from being able to map all the galaxies in the universe. So, this is one source of information. Here, if we keep going back in time, when the universe was around 300,000 years old, 380,000 years old, then and there's this fossil. The colors are a bit randomly scattered here, so sorry. So there's very brief period in which the universe gets cold enough that atoms get bound. So you start forming hydrogen atoms. And then photons start free streaming. So before that, the universe was pretty hot, like some hot plasma, and things are in thermal equilibrium. And then when the universe is around 380,000 years old, then these primordial photons start free streaming. So this is the microwave background, which I hope for your education that you've all seen a photo of the microwave background. Well, this is a battery of a cell phone that you can go to Pisa, and for 10 euros you can print whatever you want. So I took the map from Planck and asked the lady to print this for me. And she asked, what is this? And I explained, and then she just lowered her head and printed. Didn't want to talk to me anymore. But anyway, so this is the map from Planck of the temperature fluctuations. There are blue spots and red spots. And the average temperature of the CMB is around 3 Kelvin with small fluctuations. So the difference in temperature between a hot spot and a cold spot that you see in the Planck map, delta T in units of T bar, is of order 10 to the minus 5. We're going to go through this. So this is cartoon, okay? We're watching the trailer of a long movie. Okay, so I'm just giving you a cartoon of what we're going to talk about in the lectures. There are equations, eventually. So these temperature fluctuations look randomly distributed in a random map, and they give us a huge amount of information. We can infer the existence of dark matter. We can infer the existence of very special initial conditions at the putative beginning of the universe. That's where the title of the lectures comes from. And most of the cosmological parameters, the Hubble rate of the universe today, it can be inferred from detailed measurements of the CMB. So here the universe is around 380,000 years old. And then if you keep running the clock back, then you get here to time equals 0. So this, let me put 0 with quotes. It's a bit confusing. So we call this the Big Bang. But maybe the technical way of referring to it is to call it the hot Big Bang. So this is the moment. So when you read popular accounts of the Big Bang, you talk about this primordial hot soup, this messy plasma, and so on. And this is where we call time equals 0, the hot Big Bang. But well, I drew this to proportion. So I mean, there is something before time equals 0. But in the standard picture of the Big Bang, here, in order to explain these observations, you need to put correlations over long distances. And that's a huge puzzle. Okay? So how do you infer that? So these are random maps. So what you can do is you can ask statistical questions. Okay? So one thing you can do, for example, here, bad blackboard management. So here, what you can do is you can plot so the galaxies are distributed in three-dimensional space. So what you can do is you can fix some separation in the sky and compute the two-point correlation function. So you compute, if I have an overdensity over here and an overdensity over there, what is the probability of fixed separation that if I have a bundle of galaxies here, I have a bundle of galaxies over there, okay? So you just take the map of the sky, you fix some separation in the sky, you take the number of galaxies on point A, on point B, you pixelate the universe, you count galaxies, or you count the mass of the galaxies in that bin, and as a function of separation in the sky, you take the product of this. So this is the two-point function of galaxy density. So it's a proxy of the amount of dark matter in a given region as a function of separation, okay? So we are grown-ups, so I usually write separation, but we know better than that. So there is it's the distance between the points, but working assumption is that the underlying theory of the universe is translation invariant. So when there is translation invariance, you usually go to momentum space. So here I talk about the wave number. And because of rotation invariance, it doesn't depend on the direction of the wave vector. So this is the absolute value of the wave number. By the way, I'm sure I'm gonna forget to, so I'm definitely not organized enough to explain notation to you, but this appears so often that maybe let me just disclaimer. So when I remove an arrow from a vector, I mean its absolute value, okay? And we're gonna call this energy. Maybe it's premature, so you probably shouldn't like this, for me to call this energy, but we're gonna do it. And by the end of these lectures, you're gonna agree with me that it's a good idea, hopefully. Otherwise, I didn't do my job. So this is just a bit of notation. So here I just mean the absolute value of this wave vector. And if this was like a completely random map, maybe you wouldn't get anything interesting, but you get a very interesting curve. When you compute this, you get a curve that goes up, goes down, it bobs, and so on. It's not drawn to proportion. So you take a whole cosmology class to decode the meaning of this curve. It knows about the periods in which the universe is dominated by radiation, it's dominated by matter. There's some acoustic waves going on. So it's all in this curve here. And you can do similar type of plot for the microwave background. The microwave background, because there is almost no depth, it's a kind of instant in time. You go to the celestial sphere. So in the celestial sphere, you talk about multipoles. Okay? So here it's angular separation in the sky. Here there's angular separation redshift. So there's some 3D notion of separation. Well, here's 2D. So then we usually talk about multiples. So there's some principal quantum number of spherical harmonics. So of course this is a function of k. And here you're gonna look at the temperature fluctuation. So this, let me call this delta t. The two-point function. So if I have a hot spot over here, what's the probability that I have a hot spot over there? And plot this as a function of multiples. And you get, again, an interesting curve. The curve actually starts flat. It has these peaks are much bigger. you have these beautiful peaks, and then it has some damping tail at large L's. So your job is cut out for you to explain these curves. And that's where our standard model of cosmology comes from, that it has the name, the not very exciting name, lambda CDM. It's a standard model of cosmology. It just means that you need a cosmological constant that people have decided to call dark energy. It's really a cosmological constant. And cold dark matter, okay? And this, even though this is the name, it misses 1/3 of the content of the model. So my suggestion is that it should have this name. So it makes it much more readable. So this is lambda CDM initial conditions. So you need very special initial conditions. So it's not just that you need this funny dark sector. You need dark energy, you need dark matter. You also need very special initial conditions, because the fact that you see hot and cold spots or over densities and under densities means that through gravitational collapse there were seeds, inhomogeneities. So the universe was not perfectly homogeneous. It was inhomogeneous enough so that you create some potential wells for matter to fall in, cluster, and form structure. And these guys are tracing this and telling you about this. Here, you kind of see the initial conditions sort of in visceral, raw form, because that's what is low L is large separation in the sky. Large separation in the sky means stuff that is so far apart and the universe is so young, just from causality, they haven't had time to evolve, okay? So here you see some glimpse of the type of initial conditions that you need. So at the hot Big Bang, you need some two-point function of, here it's the gravitational potential, because you want to form gravitational wells and so on. So we're going to call this zeta in the lectures, but you should really think of this as the local scale factor. So the universe is rather homogeneous, but there's some slightly mismatch on the scale factor. At some points, the universe is a little bit bigger, some points a little bit smaller, and the modulation on the scale factor is controlled by this variable zeta. One way to think about it is that usually in FRW space, in homogeneous cosmologies, everything is characterized by some scale factor, some function A of t that over time tells you how much the rulers are being stretched. And the idea is that you have some small, very small perturbation that depends on space and time, okay? So these points and this point might have slightly bigger, slightly smaller universe. And characterizing the correlations of this field zeta, if you're wondering which Greek letter this is, it's zeta, so tells you about the initial inhomogeneities. So you put this hot plasma, this hot soup, on some surface that is slightly curved, and that runs the show, okay? Here, because it's in 3D, we go back to our wave vector, and it turns out, I'll explain to you in the lectures, that it's better to multiply this by k cubed because of scale invariance. And then you get a very boring, almost featureless curve. So the curve is characterized by two things. It has almost equal power at all scales, but it has, if I did my job well, you're going to realize that these lines are not parallel. It has a tiny inclination, has a little bit less power at short scales compared to large scales. And this is what you need to explain the data, okay? So these are two parameters. So lambda CDM, you need to know something about the cosmological constant, you need to know something about dark matter, you need to know something about standard matter. And then you need two parameters out of 6 to explain the universe that are related to the initial conditions. And these two parameters are associated to the height and the inclination of this curve here, okay? So we're going to try to make sense of this. I hope this bothers you. Because if you're like, okay, I just draw these two numbers, let's go home, we explain the universe, then I have nothing to offer to you. So if you're happy with this picture, then okay, we can go home. But this should bother you because this is time equals 0. So how the heck do you have correlations over large separations at the beginning? Who put that there? Who correlated things at long distances? There was some even earlier puzzle that is related not to fluctuations, that is related to the fact that the CMB is homogeneous in the whole sky. And if you just draw light cones, then you see that there's something funny going on. Like, I mean, if I take from time equals 0 and I shoot a light cone, okay, then you see that just from causality, these 2 points, if this was really the beginning of the universe, these 2 points had nothing to do with each other, right? So the temperature here could be wildly different from here, and yet they're not. And by the way, do you know what's the separation? Yeah, question. 380,000 years, more or less. So light had 380,000 light years to propagate. In a curved geometry, you can take that into account. This is a conformal diagram, like a Penrose diagram, so I'm drawing it in straight lines. But in curved space, you would have some bending and so on. So it means that there's some angular separation beyond which these points had no right to be correlated. By the way, does anyone have any idea what's the angular separation? Do I need to go here and look over there to be bothered? Do I need to go here and look there to be bothered, here and there? What do you think? Who thinks it's very large angular separation? Raise your hand. It's disposed that nobody answers, right? So there's no abstentions, you need to vote, okay? So you have to, it's mandatory. We're in Brazil. No, voting is mandatory, if you didn't know. Otherwise, you pay a fine. So do you think it's large angular separation? Raise your hand. Very small angular separation? Okay. Oh, okay, you're right. So the angle, that was not, I thought got you. The angular separation is around 1 degree, 2 degrees. It's the typical size of the hot and cold spot in the CMB. Okay? So the universe is so young that if you just move in the sky around 1 degree or so, then these points are completely disconnected causally in the standard picture. So you need to explain how to put these guys into causal contact with each other. And we have a picture. Wow, so you can see where I'm going, right? So how do you explain this? The standard hot Big Bang, there is really a beginning of time because there's the assumption that the universe is expanding. It's expanding, but it's decelerating, right? Because it's filled with ordinary matter, radiation, matter, and so on. So if you keep pushing, so the universe now is cold, but if you keep pushing the clock backwards, it gets hotter and hotter. At some point, it gets infinitely hot. So there is really a time equals 0. So the way out is to postulate that there is a funny type of matter that gives you more time. Gives you more time and allows you to push back this beginning of the universe. So the matter is unusual. But now, because we're all wise, it's not very different from this type of matter here. Some cosmological constant type of thing. And what it does is it gives you more time. So what you do is you make the universe undergo accelerated expansion. So usually the universe is expanding but decelerating. That's the standard hot Big Bang picture. The cosmological constant that we see in observations from Superiore and so on tell us that this is not quite right, that the universe is now undergoing acceleration. Okay? But it also tells us that to explain the data, the universe also underwent acceleration at its very birth. Okay? This is what we call inflation. That's what sets up the initial conditions. So these lectures are about inflation, explaining the theory of inflation, how it sets up these initial conditions here. And here, there are dragons. We have no clue. We don't have probes also. Okay? So here you could wonder, there's some initial singularity. Unfortunately, we don't have the theoretical tools, and even if we did, it's not clear we would have experimental, observational, accessible consequences here. In some sense, we only observe a fraction of the sky. There's only one universe to observe. So it's not clear. We can push back the clock. We can learn about this period, but it's not clear we'll ever have access to the global picture, because there's only one universe to observe, and our universe is accelerating now. So you could say, oh, I just wait. I'm very zen. I'll wait billions of years, and then I'll see the whole universe. The light cone grows. Unfortunately, that's not true. The universe is accelerating, so there will be a horizon, and you're not going to be able to see infinitely far away. So that's reality. So maybe we'll never learn about the true beginning of the universe. But at least we can push the clock backwards a bit further. Okay? So what's the physics that gives rise to this correlation? It's the same physics that I think you learned from Chiara, the physics of Hawking radiation. In fact, you could say that the Hawking effect has been seen. It's what explains our existence. The same physics of Hawking radiation is the one that is responsible for these primordial density perturbations. In this accelerated cosmology, you have a horizon. The geometry has a horizon. So if you're here and you have a friend, if you wait long enough, you lose contact with your friend forever. So there's a horizon. Can be useful sometimes. So there's a typical distance scale beyond which you fall out of causal contacts, and no matter how much you move, you're never going to be able to fall back in. And the idea is that over these distances here, there is a lot of particle production. There's a violent particle production, and these are the ones. I see that the picture is now very busy, but you're going to see particles being produced, and they are correlated over long distances. They change a little bit the stress energy at long distances, but they were locally sourced. So you explain causally where these correlations are coming from. It's just particle production. These particles are being stretched by the expansion of the universe, and they deposit a little bit of curvature mismatch between the points. Yeah.
So you would expect that space was also like a singularity there as well, and you could expect everything to be correlated there as well.
It is true that things are blowing up, but you can just compute the integral, even though the scale factor is going to 0, so the universe is shrinking to 0 size, there is some integral that computes how much this separation is, and the integral converges, even though the scale factor blows up. Okay. So it doesn't, you could say, well, you know, things are getting to 0 size, so it saves you this causality puzzle, but you can compute how much photons have traveled throughout the history of the universe as an integrated quantity. And in the standard hot Big Bang picture, this integral actually converges, even though the scale factor is going to 0 at time equals 0.
Okay, so one more very basic question. I thought that inflation came after the Big Bang, but your schematic says...
Well, okay. So that's the terminology confusion. So this is the Gamov, alpha, beta, Gamov Big Bang from the 60s. Then now we call the hot Big Bang. And then this, I guess, one should call the Big Bang, the true Big Bang. And here we have no clue of what's happening. Okay. So it's unfortunate. It's because we thought that here was the Big Bang, and now we walked back our statements. Here's the Big Bang. So it's not that we created two different. Okay. Here there are less exciting words that you attach. You call reheating. The universe has to heat up and so on. But
okay, all right.
In the old picture, this is what we would call the Big Bang. Yeah. I can't, yeah.
Does this mean that particles could not be entangled during inflation?
The particles could not be what?
Entangled.
I mean, these correlations generate some entanglements, sure. I mean, the inflationary, the idea is that you have spontaneous particle production, but this creates a very entangled, so you see that you have these correlations over long distances. So if I only observe some patch of this region, there is a lot of long-range entanglements because, for example, this picture is getting very busy. So let me go here. If I have here, I have all these pairs being produced, okay? I have a pair here, pair here, pair here, pair there. Okay, so these are pairs of particles. Now say I only observe, I don't know, I only observe the upper half of the universe here. So you see there is entanglement, so there is entropy associated to this because these are bits that I don't have access to. So it's a funny entanglement pattern that you don't see in flat space. But there is long-range entanglements because of this cosmological particle production. Yeah. Everyone is happy? Well, if you're not happy, that's what we think the picture is. Now, let me just, I'm definitely not an observational physicist, but let me just tell you a little bit about, you could have, I filled this part of the board with equations, but you could have asked, well, what about between here and here, before the first structures are formed and after the CMB photons are emitted? And this, I claim, is the holy grail of cosmology, okay? Here we can't see anything, but in principle there is a huge amount of information because the universe is still very boring, structures haven't formed yet, and these, if you could measure the distribution of matter and radiation throughout this whole era, then the thing to keep in mind is you have roughly 1 million CMBs worth of data. So this is typically called a 21 centimeter signal. So what happens is that the universe is just boring neutral hydrogen. And the CMB photons, they're traveling towards us. But sometimes they get absorbed by this neutral hydrogen and re-emitted. So there's some specific hyperfine transition of the hydrogen atom. And if you could detect this 21 centimeters radiation, you would get essentially at every redshift a whole CMB worth of data. And it even has some advantages over the CMB. Here you see, why is the CMB running out of juice? Because, well, maybe I didn't draw it well enough, but this is an exponential damping tail. If I go to, you could say, I just do better, I have better glasses. I look at smaller and smaller angular separations. Unfortunately, you need to beat an exponential because the correlations are getting washed out. This is physics of diffusion damping here. This physics is absent here. So you could even go to very small angular scales, different redshifts. So here there's roughly 1 million CMBs of data. Unfortunately, we can't measure anything from this so far. Well, because 21 centimeters should tell you why. I mean, a rod like this emits in 21 centimeters. Your radio emits 21 centimeters. So the Earth produces a ton of signal. It overwhelms this. The galaxy also produces a ton of signal. The CMB is very clean because if you have microwave eyes, the universe looks like a fireball. There's no other foregrounds contaminating it, at least at the level of these fluctuations here. But for 21 centimeters, we have to beat huge foregrounds. So people even talk about going to the dark side of the moon, okay, putting a telescope there to beat the Earth. So then you only need to beat the galaxy. And there are many people actively looking for this. There was a claimed detection of the monopole, just the average radiation, at lower redshifts, a bit closer to here. That's disputed. So anyway, the thing to take home is that humans, in principle, have the ability to probe our universe a factor of order 1,000 better than we can probe today. So cosmology probably still has a lot of juice to be squeezed in the future. The immediate future for your PhD and your early career will be here, galaxy surveys. And that's going to improve our cosmology, if you're an optimist, by probably a factor of 10. Okay? Very good. Well, you could ask, is there something else? Then people talk about gravitational waves, direct detection of gravitational waves. This I don't have much to say. Maybe. Okay, maybe. Well, I'll show you that inflation also predicts gravitational waves. They're the growing pains of the early universe. You know, the universe expanding and stretching, shearing, it produces gravitational waves. And it's actually easier to hunt for them not through direct detection, but through the imprints they leave in the microwave background. And we haven't seen them, but we're actively looking for them. Okay. Let me give you some numbers to explain the data. So the first real formula of these lectures. So this two-point function. This is a dimensionless quantity, so you don't need to ask me in what units. Zeta is dimensionless. So it has some amplitude, and it has some small dependence on scale, so you take some pivot scale, because we only observe the CMB over some range of scales. You take some pivot scale, that's more or less a man chosen, humanity chosen, and it has some small scale dependence that for bizarre, there are many things that we use notation that exist for bizarre historical reasons. So this is a very small number, it's almost scale invariant, but we write it as a number close to 1 minus 1, okay? Anyway, there's no history lesson today, but so that's the parametrization. So these are the two numbers that you need. And from Planck, from 2018 or so, then this is one of the few experimental observational data that will appear in these lectures. Everything else will be beautiful and analytic. This has error bars. That's kind of neat. Error bars for quantum gravity. So this 10 to the 9 is related to the fact that the typical fluctuations are order 10 to the minus 5. So the square, the two-point function should go like 10 to the minus 10. So, okay, this is 10 to the minus 9, but okay, it's factors of pi and blah, blah, blah. So. And NS is, as I said, number very close to 1. Okay. So with two numbers, it's hard to say a lot about this period, but we'll be able to say something. Okay. So the obvious question is, well, who ordered this, right? So what is, so natural questions that should spring to mind is, so what is responsible for inflation? Okay, and how do we probe it better? Okay. So these are natural questions. Can I erase these details here, everyone? Is it okay? So I remind you, Tuesday there's a colloquium by me actually. So 4:30. So Thursday there's dinner at 7:30. I don't know where dinner is, but I'm sure it's going to be good. And your short talks, you need to send the PDF files to anayelam@gmail.com. Okay? Thank you for your attention to this matter. And now I hope you didn't get the joke, but unfortunately, these days. Okay. So, what are the main probes of inflation? So I'll define inflation in a little bit, but it's roughly accelerated expansion, inflation. It's actually hard to really test this hypothesis that the scale factor undergoes accelerated expansion because you need some tracer of the background geometry. And if you wish the whole meat of inflation, it's kind of peculiar because inflation was developed to explain why the universe is so homogeneous. But because of this quantum mechanical effect, this cosmological particle production, it explains also the seeds for structure formation. And this is why people care. So this is something very important. In the 80s, it was first developed to explain this homogeneity of the universe. But then you study quantum mechanical effects and it gives you this gift. It gives you for free a theory of structure formation. Like, oh, okay, so we're sold. And it's calculable, it's weakly coupled, you can compute things, and yeah, it's probably the only game in town we have for structure formation at the moment. So how do you probe it better? So we talked about the two-point function, but you could ask, well, what about higher point correlations? So that's going to be a main focus of our lectures. You could ask about, well, are there other fields beyond the field responsible for this curvature perturbation? You could ask, what if I do correlations of other fields beyond the gravitational field? And you could look for primordial features. This I'm not going to say much about, but I mean, this is a very boring curve. You could imagine fiddling with it. Let me add a modulation, let me add a spike, let me draw a dragon here. So can I probe it? And if I have a theory for that, how do I test it? So this is what this goes under. So in the timeline there, so now I'm going to shift by 90 degrees. So now this time goes up. This is end of inflation. For the rest of the lectures, late times is going to be end of inflation. So time equals 0 in the standard Big Bang. So we're going to forget about this beautiful stuff and just focus here. Because this is where quantum mechanics and gravity play together in an important way. So to explain the observations, all we really need is this two-point correlation function of the primordial density fluctuation. And, well, you could ask, what about correlations of other fields? So I mentioned one. Now, you know, it's a gravitational theory, so they're gravitons. They're gravitons, so you could wonder, what about the correlation function of the graviton? And what about if there's another field that we don't know? And cosmologists give it a great name, isocurvature perturbation. So it's just some other field that you don't know about. Can we look for it? And it's a kind of interesting experimental facts that we see no evidence for such other. You could imagine that there are other fields that are active during inflation, and we can rule them out. If they're more than 10% of the size of this two-point function, we should have seen them already. Okay, we don't see them here. We're pretty sure that it needs to be there because of the gravitational theory, otherwise what are we talking about? So this one is forced on us, and we haven't seen it. We have maybe more stringent bounds on this. It's very interesting. I'll tell you what we learn later. And, well...
Sorry, can I ask a quick question?
Yes, yes.
So what does it mean to measure correlation functions of other fields? What is the setup?
So the idea is that you have different tracers. So you could, for example, ask, to explain the two-point function of galaxies versus the two-point function of photons, do I need two different primordial two-point functions of different amplitudes, you could imagine that photons don't couple to this guy directly, they couple to some field 1, and this guy couples to some field 2, and then that's how you would be able to tell that there's a second active field responsible for the fluctuations we see. So we see no evidence of this guy through that. That's why we call isocurvature. So to explain every observation, all we really need is one field correlated over long distances. Okay? So you could imagine a scenario in which the fluctuations of photons and baryons, they respond to different primordial fields, and then you would need two separate guys here at the beginning. So that's, yeah.
Aren't gluons and W and Z bosons light in the early universe?
Yes, but we're going to get to why we don't see them later. All of these things are vectors, and inflation is not very good at producing them. So inflation is very good at producing scalars and gravitons, but because we are in 4 dimensions, our universe is not very good at producing spin 1 particles. And actually that's, okay, maybe I'm jumping ahead of myself. That's a bit of a puzzle because there is evidence of correlated magnetic fields. We don't really know if they come from late universe things or if they have to be imprinted there at the hot Big Bang. And we don't have a good theory to produce them. You need to do crazy things during, you need to do very baroque things during inflation to generate them. And yeah, anyway, so let me, it's an open problem, how do you produce them? So it's an interesting question how you would see the standard model, but we think that to see the standard model, we need to use these yellow curvature particles as probes, and the standard model appears indirectly through tree or loop-induced effects, and that will appear here. Any other questions? Okay. So correlations of other fields, you could, for example, study the 3-point function. And then at 3 points, there are many different scenarios for what could be going on here in this blob. Okay? One possibility, let me open this up. One possibility is that you exchange at 3 level some new states. So you can use these correlations as a particle detector. Maybe this particle is very heavy. It gets redshifted away by the expansion of the universe. But it dies with a hooray. It leaves some imprint and decays. Okay? So this you could imagine probing. You can just probe for self-interactions, so you learn about the nonlinear theory of this curvature perturbation. You could, for example, related to Tarek's question, maybe this particle is a singlet under the standard model, but then the standard model fermions run in a loop here. So that's the way you could imagine seeing the standard model in the sky through these correlation functions. So I'm gonna mostly teach you how to think about these 2 cases here in the lectures, because here it's kind of state of the art. Even to compute these loops in detail, in inflation and so on, we're developing the tools as we speak today. Okay? All right. So, well, what's the theory thrust? So why do we care about this? Well, these are the equations that describe the beginning of the universe, so I think it makes sense for us as theoretical physicists to be interested in them, describe the beginning of the universe, so we should understand them as well as we can. To compute these things, it pushes our theoretical toolkit. Quantum field theory in curved space has been a subject under development depending on where you count, from the late 60s, early 70s. And the focus in the beginning was on different things like expectation values of composite operators and so on to compute back reaction. And this type of precision computation of correlation functions is something that only started actually, right after inflation appeared and people realized that you can explain structure formation, people tried to compute these things. But it took maybe 20 more years to understand how to precisely do this. And in the past 20 years, we've been developing this further and further. This was just computed for the simplest possible process. And now we understand at tree level how to do things infinitely better than even 5 years ago. So it allows us to develop our toolkit of QFT in curved space-time. And it's probably only so far the only place in nature where quantum fields and GR play an equally important role. Okay? And to compute this well, we need to have some intuition coming from different areas of theoretical physics. So it's kind of fun. You learn about conformal bootstrap, you learn about scattering amplitudes, you need to use effective field theories. And even though there's no holography, here, holography as a conceptual framework to think about this, ADS, CFT, and so on, is very useful. I'm going to make some comments about that. I think Gio's lectures might be also about holography. So let me maybe make a comment about this before I carry on. Well, this is a bit more speculative, but this network is called HoLAGrav, right? So I think holography is something that everyone here probably cares deeply about. So holography, of course, is best understood in asymptotically ADS spacetimes, where the asymptotic structure of the space-time looks like this little universe in a can with this gravitational potential. And we trade computation of some interesting process going on here, like black hole formation or some planets orbiting around each other. We can trade it by some interesting questions in quantum field theory, with G Newton equals 0 at strong coupling. So of course it's a beautiful it's the 21st century Fourier transform, because it maps some problem in gravity to a problem in quantum field theory. And it's a completely amazing change of description of the same system, and allows you to learn about QFTs at strong coupling by studying planets orbiting, and maybe allows you to learn about quantum black holes by studying questions in field theory. It's fascinating, amazing. I have nothing but good things to say about it. When it comes to flat space, the story is less rosy. In flat space, if you want to compute scattering amplitudes, well, there is some sort. In asymptotically flat spaces, you could wonder if there's some sort of holographic dual following the same spirit of ADS-CFT, some holographic dual, there's some QFT in some sort of manifold that resembles the asymptotic boundary of flat space. So people talk about celestial holography or Carolian. So the idea here would be that you either go to the celestial sphere or you go to this funny null cylinder and try to put a quantum field theory there. This is a work in progress. It's not clear that this program is going to work, but there are lots of smart people thinking about it. Maybe let me just mention that there is some sort of holographic dual of flat space, but it uses matrix models. I think that maybe Tarek will tell us something about matrix models. Is that true, Tarek? No, it's not true. Okay, but if you want to learn about matrix models, Tarek is over there. So yeah, I'm sure he'll be very happy to tell you about them. And this is the emergence of space-time is much more difficult to understand, but much more spectacular here, because you have quantum mechanics, so all of the dimensions of space-time emerge from this. So you can imagine that computing, here you work hard to see one dimension emerging. Here you have to get 10 or 11 dimensions emerging out of it, so it's much harder to relate to this type of problem. It's an old story, but maybe it's worth, given that lots of people are thinking about it, worth revisiting. Our setup here is naturally holographic, well, just in the sense that the observable is in some asymptotic boundary. So if you wish, you could imagine some way of deleting this and having some theory or some picture that is intrinsic to this surface, some rules that are intrinsic to the surface, and trying to bootstrap your way or through some rules of the game to think about some structure that is natural to this reheating surface. And we haven't really had much success finding such structure. There is one example that involves higher spin gravity that one of your distinguished lecturers that hasn't arrived yet discovered. That involves some very funny, it's not general relativity, it's some higher spin theory, for which there is some way of thinking about the resulting correlation functions intrinsically from the point of view of this surface. But even if we don't have concrete examples, it's very useful to try to anchor yourself here and ask questions intrinsic to this surface. We're going to see how that works in examples, okay? Actually, maybe towards the end of the lectures, I'll try to offer some speculative, but with formulas, way of some structure that emerges here that seems to know about this bulk spacetime. So something I was working on the past few years. Okay, so I'm done with the general introduction. I hope you're very motivated. Otherwise, I can't motivate you more. We're gonna start doing like formulas and do things systematically. Are there any questions? No. Okay. I hope you're reading your laptops about these lectures. I would really appreciate if you did not keep them on, unless, because it distracts me and your friends around you are looking at your laptop instead of paying attention to the lecture. Okay. So let me go through some basics of quantum fields, of quantum field theory in curved spacetime. What makes quantum field theory in curved spacetime a little bit different than in ordinary flat space? So there's a nice textbook that reviews this by Mukhanov and Vinitsky. So I highly recommend that you take a look. I can write the Mukhanov. I always like to do this introduction. I think they perfected the way of doing it. I'm mostly going to imitate what they do in their textbook. So the idea, curved spacetime just mean, well, high occupation number, right? So you take, there is some underlying theory, and you take some state with very high occupation number, it sets up some background, and instead of working with the original theory, you try to study quantum fields on top of this theory to understand back reaction or to understand correlations that are induced by this background. And there are two general features. The first one is that the notion of vacuum is ambiguous. There's some. And the second one is that there's spontaneous particle production. So you get out of nothing, you get particles. So the quintessential example of this example is a simple harmonic oscillator with a time-dependent frequency. Okay? So, as it can't get any simpler than that. Q of t in 0 plus 1 dimensions, the simple harmonic oscillator. I think we all agree we know how to do that. But there's a new quirk, so there's depends on time only, q dot squared. But now you set up a curved background. So here, curved background just means that I make the frequency of the oscillator time dependent. I'm an experimentalist and I dial some knob and I make the frequency time dependent. So the Lagrangian is quadratic, very simple, only depends on time. There's 1 degree of freedom. There's nowhere to hide. Okay? So we know how to quantize this. So let's say that this u of t looks like this. With this crazy stuff here in the middle. But then at late enough times, let's call t out, it looks like a simple harmonic oscillator with fixed frequency, and at early enough times, t in, it again looks like a standard harmonic oscillator with omega squared. Okay? So, before you quantize anything, you should understand the classical system. So let's quantize this. So this is, you're like, oh, this is pretty dumb. I can do that. But there will be some interesting thing that we're going to learn. So the classical equation of motion is q double dot classical of t plus u q classical of t equals to 0. And then, if you solve the classical equation of motion, you know how to quantize. You take the operator q hat, and you write q classical A plus q classical star. It's a real field, A dagger. A dagger have commutator 1. And therefore, the Wronskian of Q classical star should probably be I. Agree? Everyone is happy with that? It's good that nobody listened to him because he's killing the punchline. So ignore his question. So you have to decide which classical solution to quantize. So this is pretty standard. And well, then you say, okay, let me go to very early times and solve the differential equation, because here we know what the solution is. So for t less than t in, q classical is going to be e to the plus I omega t plus alpha. Or maybe I shouldn't call it like this. Let me call C1, C2. Right? So, I mean, we know when we quantize the harmonic oscillator that we should pick, and I always get the wrong one, we know that the right answer, so Tarek's question is, oh, what solution do I pick? Has to do with initial conditions, but the right answer is Q classical of t equals e to the minus I omega t over square root 2 omega, okay? Why? Why is this the right answer? I put you on the spot. Is this a harmonic oscillator? So you have to be able to answer this. Why? Yes, yes, thank you. So you want, so if this is the vacuum, you want to minimize. So this is the answer that minimizes. So if you want to call this vacuum, you should minimize the Hamiltonian, okay? So if you minimize the Hamiltonian, it's kind of a simple exercise. You can take linear combination of these guys, you normalize the Wronskian, and you put it here, you compute the expectation value of the Hamiltonian, and there's a vacuum, where vacuum is defined the usual way, the A is 0, 0. And you see that this is the answer for which you get the lowest possible energy, the usual half of omega. Okay, so you're like, okay, I'm pretty smart. I know how to do it. I just take the solution for which Q classical at early times is e to the minus I omega t over root 2 omega. Let me call this in. Okay, so for t less than t in. Yeah, so this is called the annihilation operator because if you act on it in the vacuum, it destroys the thing. Well, the standard terminology is that this is called annihilation or destruction operator, and this is called creation. It's just because from this you can build the Fock space, right? And then, so I don't understand the question. Yeah, sorry. Mm-hmm. Yeah, because the field phi acting on the vacuum does not destroy the vacuum, right? Because it creates a particle. It's a mixture of, so it destroys, one term destroys, but the other populates the vacuum. So it doesn't, there's something called annihilators, but it's a rather technical thing related to differential equation. Maybe you can show me some equation after the lecture. We can try to figure it out. Okay, so that's the right answer, but you could say, no, 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 no. I arrived late, and I arrived after T out, and I want to quantize the way I would quantize the harmonic oscillator here. And that's fine. You can also do that. But the main point of QFT in curved space is that the Fock spaces that you end up with, they are different. So the vacuum for the in guy is not the same as the vacuum of the out guy. And the vacuum for the in guy looks populated from the point of view of the Fock space of the out guy, and vice versa. And that's how you get particle production, okay? I mean, the fact that you get particle production is not shocking, right? You were here, then you shook, then you let this, so you end up in an excited state. But the point is that you could have said, well, for t greater than t out, you could have said, oh, I take Q classical out of t to be e to the minus I omega t over root 2 omega. And that's completely fine. It's another definition of a Fock space. So you can, the field operator Q is always the same, but you can write Q classical in or Q classical out, and you're going to have different creation and annihilation operators. And the Fock space of the system is going to be organized, the Hilbert space is going to be organized in a slightly different way. Okay? Because in general, for generic U of t, it's not true that if at early times, you already used all of your freedom, right? It's a second order equation. You chose one boundary condition to set this to 0, and you chose another boundary condition to normalize the Wronskian. So you don't have freedom anymore. So once you settled here, it is what it is at late times. And for generic U of t, you're going to get an admixture. Okay? So that's the simplest setup. And in some sense, all of these cases, black holes, cosmology, you just have a collection of harmonic oscillators. They're subjected to this type of time-dependent or space-dependent frequencies. That's more or less all there is to it. QFT is just a collection of harmonic oscillators, a weak coupling, sorry, a weak coupling. QFT is a collection of harmonic oscillators that weakly interact with each other. So that's what we're trying to do. So Q hat, the operator Q hat, can be written in two different ways. Q classical in A in plus the Hermitian conjugate, or Q classical out A out plus Hermitian conjugate. And the map between these two sets of operators, or classical solutions, is called Bogolyubov transformation. So Bogolyubov Q classical in equals, and these are called Bogolyubov coefficients, this alpha. It's standard notation to call them alpha and beta. There's a whole song and dance about how you relate the Hilbert spaces and so on. So let me tell you, so A in and A out are not the same operator. That's essential. That's why you get different Hilbert spaces. Okay, so therefore, the vacuum for the in choice is not the same as the vacuum for the out choice. It's just two different ways of organizing the Hilbert space. So the usual assumption in QFT is that the out state, oops, not equal. Oh. The out state is just a rephasing of the in state, right? So if you open your favorite, we were discussing at coffee, if you open your favorite QFT textbook, then you say, well, the out state is just a phase times the in state, and that's the reason why we throw away all vacuum bubbles, right? When we compute correlation functions, because when you take correlation function of time-ordered operators and you divide by the expectation value, the overlap between in and out, you're essentially throwing away diagrams that have these disconnected vacuum bubbles. Okay? So the vacuum bubbles are just telling us how much of a phase rotation the in and the out states in QFT have. And that's not true in curved space. Okay, so the in and the out states, they are typically not related to each other by a phase. And this guy is the culprit. So when beta is non-zero, then this is not true. Okay, so this requires beta not equal to 0. I mean, in this really, really simple example, this alpha has a name in particle physics. I wonder if anyone knows what the name of alpha is in particle physics. You have a wave, a partial wave at early times, and at late times, you get some coefficient times the same type of partial wave. Does that ring a bell? Why? Go. A? Z? T? Ah, no, you don't count. Yes. This is the S matrix. So the S matrix is 1 over alpha. Okay. So I should have written inverse of the S matrix, but okay, this is the S matrix. So it's an interesting exercise to compute various things associated to these. The point here is just to show to you that there are two different choices of quantization, and there are really different ways of organizing the Hilbert space. So for example, the expectation value in out squared is 1. It's a Gaussian theory, it's just a harmonic oscillator. So everything, you can compute the precise map between how to write the out states in terms of the in Fock space. And this is an interesting thing to compute. You can say I'm a late time observer. I have my Fock space of particles, and I just measure the number operator in what my early experimentalists called the in vacuum. And this expectation value is precisely beta squared. So beta tells you a measurement of how many particles were produced. Okay? So they are called the reflection transmission coefficients, but it's really the S matrix and the number of particles that are produced. And maybe one last thing is that they are not completely arbitrary. They satisfy this relation, which is also known as the unitarity. It just follows from unitarity. If you just impose the de Vronskian is 1, you get this. Okay. When do I stop, by the way? Who's the 10 minutes? Okay, very good. Let me, you're like, isn't this lecture about inflation? So why is this guy talking about the harmonic oscillator? So I need to build up some machinery. So hopefully after this, you are convinced, okay, QFT in curved space is a little bit different than the usual flat space story. Now I need to set up the arena. So I set up the quirkiness of quantum fields. Now I need to set up the arena, and inflation is a slightly funny background because it's accelerating. It's an accelerating cosmology. But the acceleration needs to stop. Otherwise, it's too much of a good thing. It accelerates forever, and then there's no structure, there's nothing. Okay. That being said, because we only probe the universe at a finite range of scales, it's very useful to have a toy model of what inflation looks like. And the maximally symmetric version of inflation is the Sitter space, which I was telling you about holography. Holography works best in asymptotically anti-de Sitter spaces or asymptotically flat spaces if you're willing to do matrix models or celestial holography. Here we have de Sitter positive vacuum energy space-time. So let me review. So de Sitter is just a Lorentzian version of the sphere. So in principle, everything should be pretty straightforward, but because we use funny cosmological coordinates, because inflation is not exactly de Sitter, some of the symmetries are a little bit hidden. But if you think about it, it's just beefed up rotations and so on. So now let me talk about de Sitter, and I'll say a few things because we have 10 minutes. So de Sitter space is a proxy of inflation. These lectures were mostly in the real world, so it's 4D. Okay. I'm going to talk about 4D. It's a proxy for inflation. It's maximally symmetric. So it's the most symmetric solution of Einstein's equations with a positive cosmological constant. And we're going to study free fields. So free fields in ds. It's a collection of time-dependent harmonic oscillators. Okay? Each partial wave is just like this harmonic oscillator, time dependence. So this whole exercise was not in vain. So what is de Sitter? It's the best or the simplest way to visualize the symmetry is to think of the single sheeted hyperboloid embedded in Minkowski space, one higher dimension. So here's I don't have 5-dimensional glasses, so anyway, so this is x naught, this is x1, we go all the way to x4, and it's just the surface that solves this equation, minus x naught squared plus x1 squared. So it has an intrinsic distance scale, the de Sitter radius. So here, one way to think about it is that at the neck, it's the radius of the sphere that you have at the neck. So that's the de Sitter radius. It's in cosmology, it's much nicer to think about a time scale or an energy scale. Sorry, an energy scale associated to it. So RDS is the inverse of the Hubble scale. Okay. So that's 1 over h. So if you look at the formula, of course, it has rotational symmetry with this minus sign. So it has this SO 1,4 isometry. Okay. So it's the Lorentz group in 5D. And I can't resist. I have 5 lectures, and my plan is to be very pedagogic on the first 4 lectures, and the 5th lecture go a little bit haywire. So in the last lecture, I want to tell you about some stuff I've been doing in the past. It's more like a research seminar where I'll tell you something about how to think about these isometries for spinning particles. And it's kind of a fun thing. So it's more not so cookie cutter, but hopefully it gets you excited about some stuff that is not published and so on. So it has this funny isometries. So it's really the Lorentz group in 5D, but it doesn't have Poincaré. It doesn't have translation part. It doesn't have an abelian, the separate abelian part. So it has 10 generators. So right. So 5 Lorentz group in 5D has 10 generators. And so just like flat space, but the isometries act very differently. So because the isometries change, and we know particles, Mr. Wigner taught us that particles are just representations of the symmetry group. The notion of particle here changes quite considerably compared to flat space. And I mean, the dumbest physical reason why is that because in the Sitter space, there's a clear notion of heavy and light. Right? So in flat space, there's no scales. There's the scales of humans. Things are heavy and light in LHC units, but that's just our inability of building a bigger accelerator, right? So here, there is an intrinsic notion of heavy and light because you measure particle masses in Hubble units. So the type of particle representations that you have changes dramatically if the mass is bigger or smaller than Hubble. So we're going to see how that works. So the ERAPs change. For cosmology, we have to choose some intrinsic coordinates for this manifold. So for cosmology, we do the following. We write the metric, the intrinsic metric, just looks like F or W with some scale factor. But the scale factor is very special. Is e to the ht, okay? It's also nice to write this as a conformally flat manifold. So you go to this conformal time. So that's another way of writing the metric. And if you're ADS aficionado, this makes it easy to relate to ADS in Poincaré coordinates. Right? So just, and then I'll stop. If you take some double weak rotation, you need to weak rotate also the Hubble radius. So then you get Euclidean ADS or hyperbolic space or Lobachevsky space. There's millions of names of it. And this only covers half of the manifold. And then the time coordinate t here runs over the real line. This eta runs from -infinity to 0 because there's this blow up here at eta equals to 0. It only covers this half of the manifold. But that's typically what we need, because in inflation it's not exactly like de Sitter. So if you change the stress energy a little bit, it tends to be that this, you only need a patch of ds, and most inflationary spacetimes are actually past geodesically incomplete. So you could imagine, oh, let me continue going backwards, but you get the big crunch, or really the big bang, as you keep going backwards. So that's typically enough for our purposes. And then you see here the point of inflation, that it's just blowing up the coordinates as I go. So the 1 over h is called an E-fold. So that's when the scale factor grows by a factor of E. So to explain the universe, why the universe is homogeneous, we need delta T to be order 60 E-folds. So you can play with Hubble scale and see how much time inflation needs to last to blow up the universe enough so that it looks fairly uniform to explain what we see today. And you'll find for H typical, you'll find that this is a very, 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 very brief period in human units. Okay, but maybe I'll get back to that later. So I will stop here. We continue after lunch.
Questions?